So, okay, June, we are going to start. So
Okay.
everything is in order. So I'm going to introduce you to the assistants.
Yeah.
So I'm very pleased and glad to welcome Dr. Jun Ogawa to this event from the University of Niigata in Japan. And he's going to talk about the AC loss characteristics in electromagnetic condition of HTS cable. Please, Dr. Junogawa, I'll let you
Okay. Thank
present
you.
your talk.
Thank you for
You're
me.
welcome.
And thank you. Hello, everyone. Buenas tardes. Me llamo Jun Ogawa. Es un placer conocerte. Is it okay? Yeah. Okay. I'll
So
switch.
far, so good. So far, so good.
Okay. I will switch to English. I studied Mexican greeting for future. My name is Jun Ogawa. I'm talking in Japan. Thank you for giving me the opportunity to present in Mexican Superconducting School. My talk title is AC loss characteristic in electromagnetic condition of HCS cable. Oh, sorry. Just a moment. Yeah. Okay. Oh. This is the outline. First, I will talk about the basic AC loss characteristics. Next, the characteristic of the HCS cable, and I will introduce you to the engineering modeling I'm working on. And summary. Okay, I will talk about the motivation of the HCS cable. This is motivation. The motivation of HCS cable is to reduce the cost of construction. If you live in the jungle, you don't need a superconducting cable because the overhead power transmission can be delivered current to your home. If you live in the big city like Mexico City or Tokyo, sorry, I don't know which one is bigger. And you need high current for a new stadium or big buildings, there is a chance for the superconducting cable. The overhead transmission is not possible in urban areas. The reason is the landscape and the price of the land and the traffic and the other reasons. In these areas, the underground transmission is used. This is tunnel. The size of the tunnel diameter is capacity, so a large capacity require a large size tunnel. Okay, yeah. This is example for understanding underground transmission. The tunnel requires a 4.6 diameter here. 4.6 diameter. The current capacity of the superconducting cable is normal higher than the normal cable, and it is possible to transmit the current without digging tunnel by the direct bearing, like this. The tunnel construction takes the money and times. Why is there DC and AC power cables? For the superconducting cable, it is better to DC cable because the resistivity of superconductor is zero, which means no losses. But almost conventional power cables are AC cable. This reason is not simple. First, the power generation is done on AC, and it is easy to change the voltage using the transformer. And sine wave have a zero crossing, and it is easy to shut down. The merit of the conventional DC cable is as follows. No no effect of the reactance during long distance and high power transmission. So the power can be transmitted up to the allowable current limit of the cable. No dielectric losses. It's suitable to the long distance submarine, like a submarine cable. At the same capacity, the breakdown voltage can be reduced compared to AC cable. This reason is not is the peak of the voltage different. The demerit is simple. DC current requires the AC-DC conversion. It consumes the energy and it requires the system to convert. But solar power generation is DC and data center is DC. There are sometimes needs for DC current. On safety, high DC current shutdown is difficult because no zero cross. Next, about the superconducting cable for AC. Superconducting cable is possible to carry a large current to compare the conventional cable. In the case of AC condition, the AC loss occurs. We don't forget the COP. COP means the coefficient of performance. It includes the cooling system, and we must consider the overall loss. COP is a general cooling system at the liquid nitrogen temperature using the Stirling refrigerator is 0.05 to 0.1. To design the HTS cable, it is important to evaluate and reduce the AC loss with AC transport. Next, AC loss measurement. 20 years ago, there were a lot of paper on AC loss measurement method. Today, today I will show you how to measure the AC losses. At first, I will briefly introduce the AC losses. The AC loss can be classified into three types with electromagnetic condition. One is transport current loss caused by the AC current transport. The magnetization loss caused by the AC magnetic field. The total loss is the AC transport current with AC magnetic field. It is a mixed condition. This category is simple, but we must care the subject. For example, the case of superconducting cable, these are only transport current loss in the cable as a whole. The subject is cable, but one of the superconducting tape consists of the cable. Subject is superconducting tape. Thus, in this situation, the HTS tapes are exposed to the AC magnetic field created by the surrounding superconducting tapes. In this condition, the power source is transport current and magnetic field, so it is regarded as total loss. There are three main methods of AC loss measurement. Electric method includes four-terminal method for AC transport current loss and pickup coil method for magnetization loss. Boil-off method is estimating loss from the liquid nitrogen evaporation. Calorimetric method is partially thermal insulation and the estimate loss from the temperature rise on the superconducting surface. In my lab, we use the electric and the calorimetric method. Usually, the transport current loss in the single HTS tape is measured by four-terminal method using rectangular or spiral spiral potential lead loops. The rectangle potential lead loop is attached on the tape face, and the length of the loop must be at least 3 times the width of the tape. This is a visco tape, and this is the width. This is a rectangle potential lead loop, and it requires over 3 times, at least 3 times. I think this picture is 5 times. The infinity is ideal condition. I think that the 5 times is enough. I think that. This is the spiral pickup loop is the one on the cylindrical surface enclosing the HTS tapes. This is a spiral pickup loop. This is a cylinder. On the we put the spiral pickup loop is on the cylinder like this, and the backside is here and twisted here. And we use the GFRP foundation. This green one is everything the GFRP. The GFRP has a less heat shrinkage and no magnetism. It's an ideal material for the measurement. Pickup coil method is for the magnetization losses. Pickup coils have various shapes such as a saddle shape and a box shape. This is the saddle shape, and this is the box shape, and this one is a superconductor, and this one is superconductor. This is this photo is a box type, and this is a this is a saddle shape pickup coil. This sample is to rotate the inside of the liquid nitrogen, and this situation is a little bit strange. I think that this saddle shape pickup coil is difficult to wound the coil because usually we use a fine copper line and a 0.1 millimeter diameter, and this is the if you put the saddle shape pickup coil, and we started here, and this we put this line, and this pickup coil wound on the maybe 15 turns. It required 2 days to wound. It's difficult work. Yeah. And the next is calorimetric method. Calorimetric method does not measure much in the other lab. I think the reason is that it is difficult to measure. This method requires adequate thermal insulation to measure the temperature rise due to AC losses. We use a fine-grained and surface-treated polystyrene foam. This white one is polystyrene foam. This surface is a heat-pressed polystyrene foam. And we put on the HCS tapes is here, and this one is the thermocouple. The thermocouple is placed on the surface of the tapes and with electrical insulation, and it is clamped with moderated pressure. And the calorimetric method requires calibration. Putting an DC current to the HTS for the certain time, the temperature rise of the tape is measured by the thermocouple, Corometric constant, and the joule loss is measured electrically as the same. Changing the amplitude of the DC current, calibration curve of temperature rise to loss obtained. This figure is vertical axis temperature rise. This is vertical temperature, vertical line. This is the temperature rise, and this is the energy input energy by the DC current. Temperature rise and 1 Kelvin, and the relation is proportionally increasing like this. And it requires a time to measure because the duration time is 30 seconds and cooling down time is 3 minutes. The measurement accuracy is lower than that of electrical method, and the measurement range of the range of the calorimetric method is narrow, but it is not affected by the surrounding electromagnetic environment, and the true loss can be evaluated. This is example of the calorimetric method. These pictures are an AC loss measurement with superconducting tape inserted into the iron core. This is a conventional iron core for the transformer. It's a cut core. This part is the AC coil to apply the AC magnetic field, and we make the like this the slit, and insert the polystyrene foam, and the HCS cable is like this, and press like this. And the electrical method, like 4-terminal method, cannot measure the loss because the loss of the iron core is also measured with it. But calorimetric method is possible to measure the AC loss. These figures show the comparison between the electric and the calorimetric method. This figure is frequency dependence of the transport current loss, and this figure is the magnetization loss with DC transport current. In the left figure, feel the plot, this one, and the electrical measurement result. And the empty is here, is the calorimetric measurement result. Yeah, this part and to this part. And in the light figure, the solid line is solid line is the electric method, and the plot is the calorimetric method. These results correspond within each, which means that both electric and the calorimetric method can be measured with accuracy. This is a summary of the AC loss measurement method. I skipped the boil-off method because I never done. Electric method is high accuracy and a quick measurement, and calorimetric method is not affected by the electromagnetic environment, but it is required time and accuracy is low. We use the automation measurement system for both. Especially for the calorimetric method, this system is important. For one figure, we need for one day. It requires a very long time. Next, I will show you the characteristic of the typical AC losses. This figure is frequency dependence of the transport current losses. The AC loss per cycle correspond to one curve, and which means the hysteresis losses. We talk about AC loss characteristics in slope to the transport current. That slope of the ordinary resistor to the current is the square. In superconducting tape, slope is 3 or 4. If thin film like a YBCO tape, the slope is 4. And not thin film like a visco tape, slope is 3. We judge the characteristics of the loss by the slope. Yeah, for example, this slope is 4 to the slope is 4 means the 20 to 200, the order is increasing 4. It means times 10,000 times, and increasing. And 3 is 1,000 increasing. And if we get the slope 2, it's resistive. It means the resistivity. It's a resistivity means like eddy current dominant. We can get the characteristics of the loss component. There are magnetization loss characteristics. In this case, we apply the magnetic field in multiple directions to a visco tape and measure the magnetization loss using the pickup coil method. We rotated the tape face and tape face and tape acts and to the AC magnetic field by 15-degree segment. We report the magnetic field direction dependence of the AC losses. The magnetization loss increase with the interlinkage magnetic flux. When the magnetic field applies the perpendicular to the tape face, it means this situation is the perpendicular means this is the tape face, the direction is perpendicular. It's this direction is the perpendicular. And the perpendicular to the tape face is maximum. And the parallel is minimum. The direction of the magnetic field is important factor for the magnetization losses. These are total losses. Horizontal axis is the horizontal axis is the magnetic field, and vertical axis is the total losses. The parameter is the transport current we change. The total loss characteristics depend on the transport current loss and the magnetization loss balance. This black line is no transport current curve. It means the magnetization losses. And this part is a small magnetic field area. This line is 1 millitesla, and the transport current loss is dominant because this is it goes to here. Its magnetic field is 0. It's a constant, and this line is this part is the magnetization loss affected, and this part is a mixed condition, and to the magnetization loss and the transport current losses. And next, I will talk about AC loss characteristic in HTS cable. At first, we must image the electromagnetic condition in HTS cable. The basic information: the superconducting cable is twisted and multi-layered. If you transport the AC current in the one layer of the cable, the magnetic field consists of the circumferential magnetic field and longitudinal magnetic field. The circumferential magnetic field is this black arrow, and produce the outline outside of the layer by the axial current. Axial current means this direction current. It's a transport current is the axial current. And the longitudinal magnetic field, this red arrow, is inside of the twist cylinder, like a coil. The magnetic field consists both components. Most reports of AC loss in HTS cable measured are overall. It is possible to evaluate the AC loss from the input energy, but it includes the effect of the end. Four-terminal method cannot measure the loss of each layer of the cable because the twist structure generated a longitudinal magnetic field, and the voltage lead loop cannot accurately detect the loss voltage. To address this problem, we use the calorimetric method. This is a 3-layer twisted HTS cable to measure the AC loss in each layer. You can see the 3 layers. This is the inside of the first layer, and this one is second layer. This one is third layer, and this is the twisted superconducting layer, the outside layer, and this part is the measurement section. And can you see it here? This is the white one is the thermal insulation. It's a polystyrene foam. And this brown one is a varnish. It to fix the HTS cable. this color is not superconducting. Yeah, this is varnished color. And the current in each layer were controlled using the 3 power supply, which means each layer isolated and transport current balance and phase could be valid. This cross section of the cable, this part is the superconducting layer. This black one is the black line is this is the superconducting layer, and this is the thermal insulations, and the white one is the polystyrene foam. It requires 2 millimeter, and this point is thermocouples, and we staggered the measurement section of each layer as shown. This is first layer, and the second layer is here, and third layer is here. It's possible to measure to the all sections. And this table is specification of the HCS cable. We use multifilamentary non-twist visco tapes. The critical current is 180 amps, thickness is 0.3 millimeter, and width is 4.3 millimeter. The twist direction of the cable have an SSZ structure to cancel the longitudinal magnetic field in the cable when the all current transport in serial. Sorry. The twist pitch and diameter are affected to reduce the critical current, and the circular arrangement of the HCS tapes increase the critical current. Yeah, this part. The basic critical current is 180, but the second layer is increasing, and this part is damaged, a little bit damaged part. The critical current is a little bit small. And this table is listed the circumferential and the longitudinal magnetic field at the thickness center of each layer in HCS cable when 100 amps is transported in each tape. Too simply, the determination of the magnetic field distribution, we use the Ampere law and as a cylinder model. BC is the circumferential magnetic field, this one, and BL is the longitudinal magnetic field. Longitudinal magnetic field were produced by the transport current in the outer layer, and circumferential magnetic field were produced in the inner layer. The amplitude and direction of the composition magnetic field were affected by the change in the distribution of the transport current in each layer. The circumferential magnetic field is same direction of each layer because the direction of transport current is same. The longitudinal magnetic field is decided by the twist direction. Okay, and next. These are summary of the composition magnetic field in previous table. The longitudinal magnetic field in the first layer is cancelled here. And the circumferential magnetic field increases like this, 10, 27, 35. It's increasing with each outer layer. The composition magnetic field of the first and second layer is applied almost perpendicular to the HCS tape axis. It means that this is the twist angle. You can see the twist angle here, and the magnetic field is this direction, and this angle is rectangular. This is a little bit parallel. It's nearly parallel. Okay, and these are one of experimental result. In these figures, we can manage the balance of each layer. We change the ratio of transport current in the other layer to fix the magnetic field with transport current. In this condition, the self-layer magnetic field does not include. This is this one is the first layer, and this is the third layer. For first layer, we change the transport current balance and to the second layer and the third layer. And we change the balance, but the loss is the same level we can get it. And this is the third layer. This one is produced by the this magnetic field produced by the second layer and third layer is longitudinal magnetic field. And this one is the third layer. It's a circumferential magnetic field fixed by the first layer and second layer. And we change the magnetic field, it's same level losses. And the transport current balance has no influence on the AC loss characteristics. When the magnetic field is produced by the other layers, we regard the magnetic field as the external magnetic field. Next is to reproduce the electromagnetic condition of HCS cable. We apply the magnetic field using the magnet. This is the measurement setup. Sample is here, the twisted sample. And this is the to generate the circumferential magnetic field. We place the double stacked HCS tape cylindrically, like this. And the longitudinal magnetic field was generated by a copper solenoid coil, like this. This is in this photo. This one is the copper solenoid coil. We apply the longitudinal magnetic field by this copper coil. The amplitude and the direction of the combined magnetic field are controlled by the balance between the circumferential and longitudinal magnetic field. This is the definitions of the magnetic field direction, twist angle, and the magnetic field angle. This figure is HCS sample surface. This is the surface. And the upward direction is this one. The defined to be the direction is the longitudinal field, magnetic field. And if the inner current is transported upward, the circumferential magnetic field generated will point towards the light, this direction. The combined magnetic field will point toward the upper right direction. The twist angle is here, and define the angle between the z-axis and the twist direction. This is the twist angle, and we define the angle of the applied magnetic field is here, this one, and the angle between the combined magnetic field and the twist direction. We measure the 4 sample using the 15 visco tapes with twist angle ranges from the 5 to 20 degrees. The critical current difference within the twist angle range measured in under 5%. It's enough to compare in each loss characteristics. This one is a little bit small, but this shape is 5 to 20. This part is it's near this area. This tapes is near the effect of the critical current increase, I think that. And this is the transport current loss without external magnetic field. The loss decrease with without external magnetic field. The loss decrease with the increase in the twist angle, and the AC loss ratio between 5 and 20 degree is approximately 70. This ratio is 70% at 100 amps. As the twist angle increases, the direction of the self-magnetic field is shifted from perpendicular to parallel to the tape axis. Generally, the AC loss decrease as the direction of the magnetic field approach that of the tape axis. I will show a part of the AC loss characteristics. Because the parameter twist angle, magnetic field, direction, amplitude of magnetic field, and transport current. We have many data, and sometimes we are a little bit confused. I will show the example. These figures are the AC loss characteristics of the 10-degree twisted sample and the fixed magnetic field plotted against the magnetic field direction with fixed transport current. The magnetism AC loss appear the approximately 90 degree. Yeah, here 90 degree is here. This line, everything the peak is around here, and the loss decrease as the direction of the magnetic field becomes more aligned to the tape axis. This part, it's parallel to the tape magnetic 0 degree is it's impossible to measure, but it's this part is aligned to the tape axis. It's a small decrease it. These figures the fixed magnetic field and the transport current, and we compared their twist angle. Red one is this red one is 5 degree, and the purple one is 20 degree. AC loss asymmetrical at 90 degree. It's not symmetrical, and this part, yeah, for this part is it's other twist angle approach to 0 degree. It means this direction. It's the AC loss characteristic become more asymmetrical. The longitudinal self-magnetic field by the twist structure affect to these AC loss characteristics. Last, I will introduce the idea of engineering modeling. This part is AC loss modeling for the future. The motivation is simple. Measurement and analysis require a lot of times. To address this problem, there is engineering modeling. There is no theoretical background. This is example. We have magnetization loss data in all directions. All direction means we can change this angle and this angle. We can rotate it in the magnetic field. All angle means like this. We could rotate the visco tape face and axe in the magnet and measure. We tried modeling these results. Our new model is based on the measured magnetization loss, because the loss is affected to the intrinsic critical current distribution and cross section. This condition of the base magnetic loss condition consists of the magnetic field exposed perpendicular to the surface and parallel to the surface, parallel to the face, and this is parallel to the tape axis. We use these three models. These conditions are easy to measure using the pickup coil method, not so difficult. If you don't need the experimental result, you can use the Brandt model, and this model is a slab model. It's up to you. It's a theoretical model. In this case, the loss is very small. You can ignore sometimes, but not for the visco tape. We can't not ignore. YBCO tape, it's possible to ignore this and this one, and we use the condition of the magnetic field direction of the AC losses. This is the base magnetization loss characteristics. Red one is perpendicular to the tape face, and the blue one is parallel to the tape face, and the green one is parallel to the tape axis. I can able to derive their loss from any magnetic field. Yeah, it means if you get this point in the middle, but we can lead here by the spline method or something, linear method. Sorry, I forgot the name. Linear was spline, so I forgot that language. Sorry, yeah, spline method, and we can lead here and here and here in the middle of the data. This figure is magnetization loss when the tape face is rotated. We suggest this equation, and compare in this figure. This is the angle. This angle is 30 degree, and the blue one is 60 degree. This solid line is this equation, and the plot is the measurement result. These are correspond with in each. These results show the equation covers the magnetization loss with rotate the angle of the tape face. Next, we change the tape axis. We change this angle. We use these equations and correspond with the experimental result, like this. It's the same condition. And this is 30 degree. This angle is 30 degree and 60 degree. It's correspond with using this equation. Last, we change both tape face and X using this equation. It covered all conditions. If we have base magnetization loss characteristic and the amplitude of magnetic field and both angle fixed, we can estimate the losses using this equation. This situation is this angle is theta this angle is maybe 60 degree, and this is 60 degree, and this angle is 30 degree. It's okay, and 60 degree is okay. It covered everything. This is the engineering modeling image, and we are working on same idea for electromagnetic condition of the HTS cable. These data are still work in progress. Once this project is completed, the AC loss minimization design of the HTS cable can be easily done using the genetic algorithms. Summary. We measure the AC loss in each layer of 3-layer twisted HTS cable by using a calorimetric method. For one layer, the composition magnetic field produced by the other layer in considered as the external magnetic field. To reproduce the electromagnetic condition in HCS cable for samples with different twist angle are created, and the helical magnetic field and field were applied to measure the AC losses. The experimental result demonstrate that the AC loss decrease as the direction of the magnetic field become more parallel to the HTS tape axis. Now we are working on the engineering modeling for HTS cable. If you have interest in work, please contact me. In the near future, I hope to meet you in person. Thank you for your attention. Hasta la vista. Ciao. Thank you.
Thank you very much, Dr. Junogawa. Very nice talk. So now we have a session of questions. Tenemos una sesión de preguntas. Entonces I'm looking at the chat.
Chat, okay.
To see if some people want to ask. But I have a couple of questions on my side, no?
Okay.
So I will go ahead with my questions. So the first question is, if you just want to have the losses of the full cable, no? If you just want to measure the losses of the full cable, can you use the electrical method? Or you have to use the caloric method anyway, or you can use the electrical method?
We must think about for the sample length. It requires if you install the power cable, it's a 500 meter. It depends. Its main loss is almost no, and there is a end effect. It exists, but very small part. But for 1 meter cable, its end effect is I think there maybe 10 centimeter. It's a different characteristic in the cable. We must remove this part, the end effect, and for the whole cable, it's a 3 meter. Sumitomo created a long cable. It's a 5 meter, and they twisted, they crossed the cable because it's difficult to explain. The cable is okay. I'll show you there. Just a moment. I use here, and this is cable, and the cable, and the voltage tap is here, and we put the magnetic voltage tap like here, rectangle, and they count this end part effect. We want to know here, and they cross they count the outside. This part is important to measure because this is a big copper cable. It's a huge losses. It exists. They count these losses.
Okay.
Cancel. And because the copper cable, we transport the cable. It means it requires the power cable for copper cable is here, and this is problem. And the Sumitomo thinking that they make the 5 meter cable like this and close.
Oh yeah.
And close. And this part exists, but no, they don't count this part. I told the input energy means this part. this way. Input energy is a very input energy is possible to measure, but it counts the endo effect.
Okay.
You want to know the layer of the cable because we can manage the twist angle, and it's a parallel. Yeah, the approach is two. I think one is to reduce the perpendicular magnetic field, and the other approach is to put on the parallel, like this, parallel to the tape axis, to apply the magnetic field. And we change the twist angle and manage, and it's difficult to explain, but the approach is two way, which is better, I don't know. But I think you can see here, and the magnetic field is this part is sorry, it's small, too small.
Yeah, we cannot see the pointer.
Yeah, point is here. And the twist angle, this one, the magnetic field is 10 millitesla and 20 millitesla. And you can compare the 100 amps transport is here, and it is better. Because the 19 degree is here, the maximum 20 amps, but you put the parallel magnetic field is here. But you reduce the magnetic field in 10 amps, but at 19 degree, it increases here. We have the two approaches to reduce the magnetic field, maximum magnetic field, or parallel to the magnetic field. I don't know which is better.
So the objective at the end is just to reduce the losses, no? That's the objective, to reduce as much possible the losses.
Yeah.
I see. John, there is a question in the chat.
Yeah.
From Guillermo Alejandro Perez Lobato. How do you calibrate the calorimeter?
Okay.
Is there a standard sample with a thermocouple that is used to calibrate the calorimeter?
No. I use this is a calibration for the calorimetric method. I input the DC current at first. DC current is simple because no AC losses, not depend on the frequency. The input voltage energy means the DC current, DC current, and because we use the thermal insulation like this, and it's pressed, and the thermal insulation level is different a little bit. We need the calibration for every situation for this. Then this is the proportional increase like this. Sorry, I don't know. I've lost my point. Okay. Like this, and it's a proportional increase. It will be okay, this level. But you input the magnet much more. Much more input energy. It goes down because the cooling effect is increasing, and it will be goes down like the flat. The same level. Is it okay?
I'm going ahead with the question because there was a second part to the question. Could you use the calorimeter to measure the specific heat capacity of the cable in the transition between superconducting and normal states? This is a very specific question. So can you use the calorimeter to measure the specific heat capacity of the cable in the transition between superconducting and normal states?
Yes. It's a point for AC loss measurement. It's important. Corometric method and the boil-off method is important for us because it's a point. Important point is to keep the critical current. Because the critical current increasing, it means the AC loss, it changes the AC loss characteristics. We can see the AC loss in same time. In my experience, I think the 1 Kelvin, it's okay. The characteristics no changes. The heat capacity is there. Yeah, we don't discuss the heat capacity because this situation is like this. Is the heat capacity is difficult to count the this tape. We have a lot of tape because the visco tape has a width is a little bit different and structure is different. It's difficult to discuss the thermal condition. We use this way, like it's this point is the same condition and to measure. And at first we created the same thermal insulation and the same measurement part and calibrate, and after that we measure the AC losses. It's important for us. Is it okay?
Yes, thank you. Yes.
Yeah, thank you.
It's okay.
Yeah.
I have one more question.
Yeah.
Do you work with the industry in Japan? Because it sounds to me that this is for Sumitomo actually.
Yeah.
It's I have the impression you are doing this measurements so the industry, the companies in Japan, they can produce better cables.
Yeah.
Is it correct or am I wrong there?
No, yeah, it's a HCS cable is in Japan. It's a very difficult to create it because but I think their fusion energy cable to install their fusion. It's a AC cable. It requires this technique. We collaborated the fusion group, and the Sumitomo group is they stopped the cable project. I think that they created the coil and the cable project, and it collaborated in Japan. The TEPCO is a Tokyo Electrical Power. It's a very electric company, very big electric company, and collaborated to the Sumitomo. Yeah, we supported that group, but now they stopped everything because the tsunami was come at the Tokyo.
Oh yeah, okay.
Everything that stopped.
I see. So actually, you're working for ITER?
Yeah. Now I'm working for ITER group.
Yeah. Okay, I see. ITER, which is the fusion device for
fusion device.
Those who are listening. This is the big fusion device.
Yeah, but it requires a big current.
Yeah, sure.
It's for AC cable and the AC and DC cable. They are talking about that. Yeah, and special situation. It's like a special factory. A short cable. It requires the AC cable. They can dig in tunnel and very high current. And the next they connected the factory 1, 2, 3, and I think that some people thinking about that. The short cable for HCS cable.
I see. I don't have any other questions. I don't know if someone else, except from Guillermo and myself, have some questions for Dr. Jun Ogawa. It seems we were the only ones on this one. So, Jun, thank you very much.
Yeah, thank you very much
for being with us through video conference. So hopefully we're gonna see each other, as you mentioned, in Mexico.
Yeah.
Let's see if we can make this happen.
Yeah.
And thank you again to all the people that connected. We had a problem with the YouTube transmission. because actually I think we couldn't see on the transmission the full slides. So, but I recorded on my side the presentation. So, see if someone wants it afterwards, I can share it. If June agrees to share information,
Yeah.
we can share the video later
Yeah.
on.
It is the first time for me this in Mexican lecture.
Welcome.
Yeah.
Welcome to Mexico.
Yeah.
Yeah, video
I want to
conference.
go.
So I let you the last word, June, if you want to say something.
Yeah. Last word?
Yeah, the last word.
Yeah.
You have the last
word.
word.
It's a difficult to Mexican. Hasta la vista. Is it
Hasta
okay?
la vista. See you
Okay.
then.
See you.
See you. Bye bye.
See you.
Thank
Bye
you very
bye.
much. Bye.
Bye. あれこれだ。これ、OK. Bye bye.
Bye bye. See you soon.